Hello and welcome to the 2:30 Math workshop as part of the Oxford Maths Online Open Days. Great to see you again. It's a lovely sunny day. I've sort of wondered whether people would turn up to the math workshops, but it's great to have you here. Here's how this is going to work. I'm going to put some math questions up and a warm-up question, and we're going to try and do them together. And I'm going to use the Q&A box on Slido as a sort of chat, so you can just tell me anything about the questions and let me know what you're thinking or answer them as we go along. So it says Q&A. If you click any of the join Q&A buttons on the Open Day website, you get through to slido.com. The event code, if you want to go through Slido, if you find the Slido website and go to Ox Maths Open Day, that's maths with an S, day without an S, Oxford without an S. If you find the Slido, then that Q&A we're going to be using it like a chat box. You've sort of won the game theory decision of deciding which Matla workshop to go to, because there were slightly more people here for the previous one. So this one's going to be a little bit more cosy. I'm going to rely a little bit more on people to join in with the questions, but it's sort of smaller group, so it should be more fun. Right, okay, that's enough waffle from me. Just to check if anybody's found the Slido for talking to me, I've got a warm-up question. So I've got 2 to the x cubed, and I'd like to know what's that equal to. Can you find an equivalent expression or something else that's equal to this expression in terms of x? Okay, let's see if anybody's found the Slido for talking to me. It says Q&A everywhere and it says ask a question, but you can join in even though the things are... Yeah, see, Phoebe's put 2 to the 3x question mark, and you don't have to put the question mark, Phoebe, because you don't have to ask a question. Isaac, you put question mark in. It's fact, we don't have to pretend to be asking questions. Slido doesn't check if the thing you're asking is actually a question or not. You're all right. 2 to the 3x is a perfectly acceptable way of writing this. Oh, I've put brackets on. Why not? Other things people have said. Oh, somebody else has said 8 to the x. That's good. I like that. So these are the same, right? Because 2 to the 3x is, you could write it as 2 to the x cubed, or you could write it 2 cubed to the x. So that's 8 to the x. Somebody said 8 to the 3x, which I think might be too many 2's. Okay, let's have a quick check. What have people said? Oh, Alexis is here with 8 to the x. Joseph is here with 2 to the 3x. Brilliant stuff. Those are the first 2 people have come up with. George and E and Anonymous have joined in as well. Anything else? Could we have 4 to the power of something, for example? So just sort of workout, warm up, trying to get into shape, messing around with powers of things. Can I have it as 4 to the power of something, please? Let's see if that works out. Okay, and then if we can write it as 4 to the x, there are other things we could write it as. Okay, so maybe 4 to the something, isn't it? 4 to the, people disagree a little bit. So 4 to the 2x would be 4 squared to the x, which would be the same thing as 16 to the x. So maybe not quite 4 to the 2x, but then George said 4 to the 1.5x, which I think does work. So I've been slightly mean that 4 is not quite the square root of 8, it's sort of 8 to the 3 over 2. Yeah, so 4 to the 3x over 2, 4 to the 1.5x. Oh, true. 4 to the, what else are people writing? 3x over 2. Okay, there's sort of a number you can write up here. Any other powers? Any other expressions that we can think of? Anything involving other numbers? Might be no other ways to write this, right? Can I write this? Maybe this is cheeky, so keep typing if you're typing, but can I write this as 3 to the something? Can I do that? Is that allowed? Can I write it as 3 to the something? Maybe I can, maybe I can't. Sort of messing around with powers. Okay, good. And I'm guessing I do, yeah, I must have, I worry a little bit about whether I've turned my sound on or not. I guess I must have the sound on, otherwise, oh, I did write the 4 on the board. Nah, someone would have said. Okay, can I have this as 3 to something, or maybe another number? to the power of something, or is that impossible? If it's impossible, you can tell me it's impossible. It's important when you're working out, when you're warming up, it's important not to try something that's impossible. So if you spot something impossible, it's important not to overexert yourself by doing that. Yeah, I was someone suggesting maybe use logarithms or something to get in there. Yeah, so people have got, okay. People have got equivalent expressions for this. If you've seen logarithms, then you'll have seen a way to write, if I want to write 3 to the power of something as this, then I should write this thing up here, I should write what do I want? I want the logarithm base 3 of all of this stuff, or something. That's allowed. 3 to the power of log base 3, 2 to the 3x. We can simplify that a little bit, and people in chat are simplifying that a little bit to say that this is equal to, am I still on the screen? I am still on the screen. 3 to the power of 3x log base 3 of 2. Okay, so there's some number. It's like 3 times log base 3 of 2 that I can write up here. In the same way, there was some number 3 over 2 that I can write here. There's just some number that I can write up here. Okay, so to sort of work out, we've gone from cubing numbers to messing around with powers, to thinking about messing around with square roots of things. So actually, logarithms give us a way to do this in general. It doesn't quite work if you require everything to be a whole number, then logarithms are a little bit messy. Which is maybe why nobody thinks about it. Phoebe learned about logarithms yesterday. Welcome to a logarithm warm-up, sorry about that. Neither of the problems I'm going to do next use any logarithms. Just sort of wake up 2:30 in the morning, 2:30 in the afternoon, time to wake up, do some logarithms. Something like that. Right, okay, I'm rambling. Let's look at a math question. Or first, I think I like exploring other things you can do with these objects as well. So when I see 2x cubed, I'm sort of thinking a little bit about cubic expressions. And I sort of thought about maybe, I could have a cubic where I have that 2 to the x and I play around with solving a cubic or something, or writing out a cubic expression using 2 to the x cubed, something like that. Anyway, just an idea. Other exercises that you could try, right? So you could combine this with, you could look at this and think powers and exponentials and logarithms and practice that, or you could look at this and think, cubing equations. Can I solve things like 2 to the x cubed equals 1 or something? That's a cubic equation that maybe I could go and solve. Wonder how many roots that's got. Wonder how many solutions there are. Anyway, right, okay. Anyway, here's a math question. This is from 2008. I scrolled a long way down the past paper questions, hoping to scroll further than anybody had scrolled so far. So I hope this is a question you haven't seen before. I'm going to talk about it, even if it's a question that you have seen before. So hopefully I can add something. What I'm going to do is I'm going to talk about it, but I'm also going to put a poll up in the Slido. So if you want to vote for your answer, then you can do that over in the Slido chat as well. But we should talk about it, because this question looks horrible. I haven't read it out yet. I'm going to read it out. And then we're going to talk about it. Remember, when you see a math question, they're not supposed to be easy. They're not supposed to be straightforward. They're supposed to be questions you get stuck on, questions you need to have an idea, questions you need to get unstuck. And I'd like to explore that today, if we can, to try and get into how you get unstuck or how you have ideas. So if you've got an idea for this question, then it's okay to post in the Slido Q&A to post something about what your idea looks like, to try and help other people understand how you got unstuck, if you've got unstuck. Right, okay. I'm rambling so that you get a head start on this question. Let's read it out. The equation 9 to the x minus 3 to the power of x plus 1 is equal to k. That equation has one or more real solutions, precisely when, and then there are some options for different ranges of k. So we're being asked when this equation, which looks scary because it's got different powers in, it's got 9 to the x here and it's got 3 to the x plus 1 here. It's got a k over there. We're being asked when it's got one or more real solutions. Okay, so we've got two letters in, 2 numbers, we've got one or more real solutions, and we've got different ranges of k. Okay, and people are already starting to put in chat their suggestions. So don't look at the Slido chat if you don't want to see suggestions of how to make progress with this. Nobody's voted for a final answer yet, but we'll get there, I think. Okay, I'll give you a minute to think about that, think about how to make progress. You can work together in the Slido Q&A chat if you want to. But I think more than just getting to an answer, I'd like to examine different methods of how you get there. Okay. it's very tempting for me to start helping straight away, right? To just tell you how to do the question. But I'd like it if you're stuck on this. I'd like to sort of stay stuck on it for at least a moment more. Big pause to stop myself from saying something helpful. People want to rewrite the terms. Yeah, okay. There's some good suggestions coming through the Slido. Let's read one of them out. I'm going to go for Bert, because I think your suggestion is the smallest clue that I can give to someone without giving away what's going on. This 3 to the x plus 1, Bert Jim in chat says, is equal to 3 times 3 to the x, which is true, but it makes this look a bit more like a 3 to the x sort of thing rather than a 3 to the x plus 1 thing. Okay. I quite like that. I think it makes, I see a lot of a to the x terms, a to the x plus 1, it's like a translation or something. I'd like to write that in terms of 3 to the x. And there are more people talking about quadratics. I'm trying to be vague. People talking about quadratics in the Q&A as well. Q&A Slido chat. What am I going to call it? I'm going to call it chat. I think people are talking about a quadratic. I suppose possibly because they've done some algebra, or possibly because they're thinking about the phrase one or more real solutions, which reminds me of quadratic equation science, where you've got a quadratic equation and you're thinking about how many solutions it's got. That's somewhere on the math syllabus where we talk about number of solutions anyway. But it's not a quadratic, is it? It's a pair of exponentials and the number k, which we don't know. So there's something else going in here. Georgie's got a suggestion. It's clever. Okay, so trying special values. I like this. Because it's multiple choice, we can eliminate options if we think about special k values or values of x. Georgie's got a pair, x equals 1, k equals 0 to plug in. If we do that, then we get, what do we get? 9 to the 1 minus 3 to the 2, that is 0. So that's a real solution when k is 0. Okay, so I suppose that rules out C and D, because C and D wouldn't permit us to have a real solution when k equals 0. Georgie knows that when k equals 0, that's compatible with x equals 1, a perfectly nice real solution. So not C or D. I quite like that approach for ruling out options. You've now got two quite similar looking options, A and B, Georgie. Maybe if you have a different choice of k and x values, maybe you can rule out options like that. How's it going in the voting? So far a handful of people have voted so far. So far everyone's correct. So that's nice, isn't it? I've hidden the results so you can't see that yet, but I can see everyone's good so far. So somebody wants to write k as a power of 3 as well. So we've got lots of powers of 3 going on over here. I guess they've spotted that 9 to the x is equal to 3 squared to the x, which is the same thing as 3 to the x squared. Aha. Maybe write k as a power of 3 as well. Does it rule out b as well? Maybe it does rule out b as well, because b doesn't include k equals 0. It sounds like a very good choice of values of a and values of x and k. Case eliminates b and c, d. It does not. D. Oh, does it not rule out d? I've got myself confused again. Most of these ranges do not include the number 0. One of them does include the number 0. Yeah, I think it rules out B, C, and D. Bit of a shortcut. Good. Right, people want to use the discriminant. Yes, about 4 people at the same time. You know it's a good idea when 4 people at the same time put in the chat simultaneously saying, let's use the discriminant. Because I guess you've spotted that this has started to look like a quadratic equation. Now there's different approaches we could use here. I think if you're going to talk about the discriminant, you probably want to move the k over onto the left, and then talk about the discriminant of this quadratic. Because it is now a quadratic. It's a quadratic in 3 to the x. So if 3 to the x is my variable, maybe if I gave it a name like u, then I'd have a quadratic, and I could throw the discriminant at that to work out how many solutions it's got. I get something like 9 minus 4, a minus c here is minus k. I want that to be bigger than or equal to 0 for one or more real solutions. And I'll get that 9 plus 4k is bigger than or equal to 0. Oh, brilliant, that's option A. K has to be bigger than or equal to minus 9 over 4. Except, let's be really careful. Because this is one or more real solutions. So but it's one or more real solutions for the variable in the quadratic, which is 3 to the x. Can anyone see how that might go wrong? I'm not going to say whether it goes wrong or not here. But can anyone see how that might go wrong? There's a sort of small subtlety or a small thing that could go wrong. I'm going to make a big fuss about it. It doesn't matter with this question. I'll give that away. It doesn't matter at all. The answer is in fact A. Let's put everyone at ease. The answer is A, and it turns out to not matter. But can you see how there's a sort of subtle issue here? Yes. Oh, one person can. Brilliant. Let's see if anybody else is typing. Let's give them a moment to type. Yeah, brilliant. Okay, a couple of people put something in the chat. The 3 to the x is definitely positive. So this condition, strictly speaking, this condition gives us one or more real solutions for 3 to the x. But if they're both negative, then, oh no, we don't get any solutions for x. What we really want is a solution for x to solve this equation, right? At the start, we want x to be a real number. So really we need 3 to the x to be positive. I mean, it is positive, but we shouldn't try and give it a negative value, right? It turns out we're okay, that this equation definitely has a positive root, no matter what k is, so long as it's bigger than minus 9 over 4. Somebody has completed the square in chat, which works nicely, I think. When I saw this, maybe somebody else out there thought this as well. When I got to this stage, I thought about drawing a graph. Because I have this k on the right hand side, I said it was optional to bring the k onto the left hand side. With the k on the right hand side, let's do a little graph corner over here. Does graph corner fit on the screen? Graph corners fit on the screen. So if I do a little quadratic like this, 3 times 3 to the x is equal to k, then the question in terms of a graph, maybe I could draw the graph on the left hand side there. It's got, I suppose, so if this is, if I call this u equals 3x or something. I'm only interested in positive u, and it turns out we're fine, because so long as k is bigger than this value, there is a solution. So if k is up here somewhere, that's fine, there is a solution over here, and we're good. It's not the case that both of these solutions end up having u negative, which is hard to see how that could happen now that I say it out loud. We're fine. At least one of these solutions is real. I guess we could fall into trouble if it asks for exactly 2 real solutions. Then the quadratic. So the quadratic has a bit of let's do this in a different color over here. The quadratic has a bit of space over here, right? If I draw the whole quadratic, there's a bit over here. But this bit's dangerous. That's why I put it in red. This bit's dangerous because solutions over here. Well, when you set it equal to k, it looks like a solution to the quadratic, but that's where u is negative, and 3 to the x can't be negative if I want a real solution for x. Real numbers x, 3 to the x is always bigger than 0. Okay, so we could run into danger if we were caught out by looking for solutions where u is negative. Perhaps if the question said, when does this have exactly 2? Then discriminant method would say always when it's strictly bigger than minus 9 over 4, but actually it's a little bit more subtle. K has to be between minus 9 over 4 and 0. Okay, for a different version of this question, to check out why that could matter, for a different version of this question, try this. Oh, I still want that to be, I just want to change the minus to a plus. Okay, 9 to the x plus 3 to the x plus 1 equals k. This has got, when it turns into a quadratic, this has got the same discriminant, so it looks like it's going to be a, but actually the answer would now be b, I think, or something a bit more like b. k is positive or equal to 0. Yeah, no, I think actually B. If I put the plus sign in, then I think the answer would become B. Something to worry about there, I think. Checking whether your solutions actually work. So what do we learn? We can learn that you can approach these questions in different ways. People wanted to... there was a different approach that I didn't really explore, where we think about writing k as a power of 3, and we try and set these powers of 3 equal to each other. Maybe think about expansions in terms of powers of 3. That could be fun. And then even once we turned it into a quadratic, there were differences about how we approach that quadratic science, whether you want to go away and do the discriminant, or whether you want to sketch a little graph, find the roots, or whether you want to do... so here I had to find the sort of minimum and find out where that minimum point is on my quadratic. Hopefully this stuff with quadratics, where you're messing around and finding the roots, finding the minimum, complete the square, find the discriminant, that sort of stuff, shouldn't be too stressful, because hopefully you've done lots of stuff like this before, so that you can find roots of quadratics and work with things like that. Okay. On the other hand, choosing what to do at the start here, where we had this unfamiliar thing, we had to realise that we could turn it into a quadratic, that's very difficult. So that's a step that we should try and put lots of brain power into, so that we've got lots of, we can relax while we're doing the quadratics, so that we can save brain power for thinking of when we're going to do a quadratic. Okay, Liz Kid and people answering in the Q&A were extremely successful. If I reveal this, does it reveal everything? Oh, let's just say everyone's correct. Everyone who answered that question in the Slido Q&A got the right answer, so that's pretty good. Let's look at another one. Here's another math question. This one looks horrible, right? We've got, we're looking for the highest power of x in, and then there's a horrible expression with curly brackets, square brackets, round brackets, about 8 different things inside brackets being added, subtracted, multiplied, powers, and we're looking for the highest power of x in this expression. Okay, I'm going to resist the urge to tell you how to do this question and let you get stuck or just stare at how horrible it is for a moment. And I'm going to check how we're doing in chat. So chat, chat's talking about negative solutions, and completing the square is, completing the square is a good way of thinking about it. You need to, I suppose, when you complete the square, you get a 3 to the x minus 3 over 2 inside the brackets, and that's good news because it means that your roots are going to be 3 over 2 plus or minus some stuff, which is going to give you a positive, definitely at least one positive thing for your 3 to the x. If it was 3 to the x plus 3 over 2, then you'd have to worry that you're doing some plus or minus square root stuff and then subtract 3 over 2. Is that positive or negative? Isaac would like to know how much each question is worth. So you do 10 multiple choice questions at the start. They're worth 4 marks each, and they're marked in the sense that you get 4 marks if you get the question right, you get no marks if you get the question wrong for those multiple choice questions. That gives you 40 marks worth of multiple choice questions. After that, you do 4 long questions. Each of those is worth 15 marks. So 15 times 4 is 60, 60 marks of long questions. That adds up to 100. So maths out of 100. So you do 10 of these and 4 longer questions. We're going to look at a longer question in a moment after we've tackled this one. While I'm talking about marks, I'll talk about marking. Talking about marking is good because it stops me from doing the question before everybody else has done it. Have I turned a poll over this? Yes, I have. Brilliant. People have started doing this question already. Fantastic. So we do, for the long questions, worth 15 marks with lots of parts. We get graduate students to go through your work very carefully and look at everything you've written and decide whether any of it's worth marks, looking out for whether you've used an exciting new method that we weren't expecting, or whether you've done something slightly differently, brilliant stuff like that. They've got a mark scheme, but they also write new mark schemes if something new turns up. I get graduate students to do it because they're really good at spotting when new maths might be true maths and deciding how many marks to give it in a fair way with the other solutions. They love it. Right, that's the long questions. For the short questions, it's that all or nothing, 4 marks or no marks. But there's a way to sort of get some marks, get some partial credit marks, which I'll try and describe. Before, when we were talking about eliminating options for the multiple choice questions, if you can do that, then you can get down to having a sort of hunch about which option it is. So if you could eliminate two of these, then you could have a kind of strong opinion on which of the remaining ones it might be. And if you then put that down, there's no risk because there's no negative marks. So there's no risk to putting down an answer for a multiple choice question. Or a long question, to be honest. No risk, just write stuff. There's no risk, so choose an option. Then you sort of probabilistically you get marks like that, and that might be a reasonable strategy if you can narrow it down until you're pretty sure it's one of the options, but maybe not totally sure. It's still worth ticking that rather than ticking nothing. Okay, that averages out as kind of partial credit. Right, okay. People have worked out some highest powers and answered my poll, which is very exciting. Oh, it looks like I've rambled long enough for quite a few people to have a go at that. Brilliant, okay. And you're all correct again. So, what am I doing? People are talking about taking the highest power from each term, which I like the idea of. So, let's talk about a bad way to do this question, which I'm sure you haven't done. If you try multiplying out all of the brackets, then there is about 500 terms, so it's really horrible to multiply out. Please don't do this. Since we only want the highest power of x, well, there's big curly brace, big curly brackets with a cubed outside, but inside we just need to find the highest power of x inside. And actually we can do that by looking at this square bracket. Oh, let's try and box a square bracket. That stuff. Let's do that with a different colour as well, actually. If I'm going to draw boxes around things, so I'm going to be a little bit more clear about what I'm boxing. Right, okay, there we go, that's better. So we can look at this stuff, and we could look at the other term inside the brackets here. And we could decide which one's more important, which one's got the highest power of x, and then ignore the other one. And say, well, the highest power of x comes from taking the highest power of x, whichever one of these has got the highest power of x in it. And then looking inside those boxes, we can work down, right? To look at what's going on inside these things. Inside here, is this red thing has this got a higher power, or has this got a higher power inside here? Okay, so we can keep comparing and building things up. We're only asked for the power of x. We're not asked for the coefficient. So we could ignore all the coefficients and just work out how big things are. I suppose this thing inside the brackets looks a bit like x to the 6. So then after I've cubed it, I'll be a bit like x to the 18, where I'm just writing down the kind of highest power. This one looks a bit like x to the 32, right? X to the 8 to the power of 4. So it looks a bit like x to the 32. A little bit more power practice. Okay, so this one's way more important. So we can just ignore all of this because it's x to the 32, it's a bigger power of x, and we're just looking for the biggest power of x. Okay, this method does. This method doesn't give you the coefficient, and it doesn't give you much of an idea about what the next term, the next biggest power of x might be. Okay, a little bit worried. I haven't thought about this 5 yet. I need to think about this 5. Oh yeah, no, I've boxed it really badly, haven't I? This purple box should go inside the... Hang on, let's fix that. I'm about to move on, but this purple box should go inside here, shouldn't it? Not that. Right, okay, we fixed it. I don't really know why I'm explaining it. Everybody seems to have done this question just fine. Anyway, right, I'm going to speed up a little bit. So then after raising to the power of 5, I'll get something that looks like x to the power of 160. All of this term turns out to not matter because this thing looks like x to the 25. This bit looks like x to the power of 28. So overall, ignore the x to the 25, take the x to the 28. That goes to the power of 6, so I get x to the power of 168. I'm doing 28 times 6. Then I've got 160 versus 168. So this 160 is not the biggest power, so we can ignore all of that. Take the x to the 168. Finally to the power of 3 to get x to the power of 504. So that's option D. Brilliant. Okay. Which I think everyone's got right again. Oh, very successful Math Workshop group over here. I love it. Right, okay, great. So sort of approach to short questions of, I don't know what I'm doing. I've got an idea about how I might start to make an approach with this. Oh, brilliant, I've got one of the options and I'm feeling happier about this all making sense towards the end. It's a kind of structure of solving a short question in a lot of cases. Loads more of them on the website. Right, okay. Let's look at a long question together. Here we go. So this long question asks us for a pair of positive integers. This is, I think, 2008 question 2. And it mentions a pair of positive integers that solve this equation. And then there's some more bits of question after there. So I'm going to give you a moment to think about that. Oh yes, so someone spotted that was an old question that only had four options. We added the fifth option to make guessing a little bit less good. We added the fifth option, I think, in 2014, a few years ago now. So it's now got 5 options for the multiple choice questions. Somebody's seen something like this before. Olivia, I'm not sure if you're in this workshop or answering a question in the general Q&A, so I'm going to type an answer to you as well as talking. If you mention a book or particular areas of maths you enjoy in the personal statements, what kind of questions can you ask about this? I guess I'll read out my answer as well, just in case Olivia's in this workshop. If you mention a book in your personal statement, then you might be asked about it in an interview, but probably not. We might ask what you liked about the book to see if we can demonstrate enthusiasm for mathematics. But we might just not mention the book and just ask you maths questions that we want to ask you. Somebody suggested some numbers, and it looks like we're going to have an argument about whether 0 is positive or not. Actually, they've retracted that. So it seems I don't have to have an argument about whether 0 is positive or not. So someone spotted that 1 squared minus 2 times 0 squared is equal to 1. Is 0 positive? I'm not sure 0 is positive. Some people think 0 is positive, so I'll let you have that. E and Anonymous have come up with 3 and 2 simultaneously. I like it when people come up with things simultaneously because it probably means that it's true. I don't have to think. There we go. Have I been tricked? No. 9 take away 8 is indeed 1. Okay, brilliant. So we've got a solution. And since this is just find a pair of positive integers, that'll do. We found some numbers that solve the equation. I guess we could talk about this, but we're sort of using trial and error, right? We're sort of guessing solutions and just trying small numbers, which is a valid way to approach maths problems. If you want to check whether something's got solutions, sometimes the quickest way is to just try some things and see if they solve it. Okay, brilliant. Some people have given that thumbs ups to say that they've also got 3 and 2. Brilliant. Okay, right. No poll for this one. I couldn't work out how to convert this into a poll. Okay, next part of the question says, given integers a and b, we're defining sequences. So these things x1 and y1, I wondered a little bit why they have 1s on, right? These are sort of subscripts that make it feel like a series. If you just look at the first part of the question, then there's no series. There's sort of no reason to have the subscripts there. But okay, now we're turning them into a series. The way the series works is that xn plus 1 is going to be defined in terms of xn and yn, and yn plus 1 is going to be defined in terms of xn and yn as well. So this is a little bit more complicated than series you might have seen at A-level or equivalent. It's not really an arithmetic sequence or a geometric sequence, the sort that you see on A-level. And actually, because of that, that means we can't really use any of the theory we know about arithmetic and geometric series. But hopefully you're okay with series defined as this notation means x subscript n plus 1. So this might be x2. If n is equal to 1, then this reads x2. And if n is equal to 1, then this reads 3 times x1 plus 4 times y1. Okay, and this would define y2. Okay, we've got these numbers a and b in here. We're going to find values for a and b now. What do we want? We want a such that some stuff. Ugh. Okay, So I'm sure people are bashing away at the algebra or having a go at doing this, or maybe they've got clever plans for how to find A and B. We want positive values of A and B. While you're bashing through doing stuff, does anyone want to explain roughly what you're doing? Is this a part of the question where you want to stop and think, or is this a part of the question where you want to sort of get on with it and do some stuff? I guess it's slightly unfamiliar, right? We've got this series xn plus 1 and yn plus 1 that's defined in a way you've probably never seen before, where each term depends on the previous x term and also the previous y term. So there's this sort of complicated behaviour that each one doesn't just depend on the previous value of its own sequence. The sequences are kind of linked together, that each one depends on the previous values of both previous sequences. But in terms of algebra, it's not too bad. It's some expression for each of them. I'll have a guess at what people are doing to have a go at this question. I think you're probably plugging in xn plus 1 and yn plus 1 into the left-hand side of that equation and trying to solve for a and b in some sense. I'm going to start having a go at that too on the board. Yeah, perfect. As I said that, there's a little bit of lag. So as I said that, I saw a message come in. Perfect. Rearrange it, expand, and compare coefficients. Sounds good to me. Okay, I'm willing to just sort of go for that, I think. There's always a moment where you're sort of making a plan and you're trying to see, is this a good idea? Is this something that I should be doing? And there's always a moment where it's sort of, you've got to actually put pen to paper and start working stuff out. So this is my left-hand side. And we're going to find out along the way whether this was a good idea, I suppose. So this is, why am I doing this live? 16yn squared. It's easy for you at home. Nobody can see what you're writing. Minus 2b squared yn squared. And I want that to be equal to the right-hand side, which is xn squared minus 2yn squared. Okay. And people in chat are saying, we can compare coefficients, which is fantastic. Comparing coefficients, I suppose, I want to look at the coefficient of xn squared. So I've got a 9xn squared here, and I've got minus 2a squared xn squared here. And I want that to be equal to 1 times xn squared. So I think I want 9 minus 2a squared to be equal to 1. And a is supposed to be positive, so I think that means a is 2. And then maybe I could look at the coefficient of yn squared. So I've got 16yn squared here, I've got minus 2by squared here, and I want minus 2. So I think that means I want 16 minus 2b squared to be minus 2. So I think I want b to be positive as well, so b is 3. Brilliant. Okay, I've got values for a and b. Do I agree with you? I think I agree with you. So look, yeah, people in chat giving me 2 and 3 as well. That makes me confident that that's the only solution. That's not an actual proof it's the only solution. I think somewhere in here was a proof that it's the only solution. But everyone's got the same numbers, so probably the only solution, let's say. There's a little bit of a coincidence here, right? That I've looked at the xn squared coefficients and the yn squared coefficients, but there's also an xn yn term, which looks like this. It looks like 24 here, and there's a minus 4ab, but kind of magically, my choice of a and b, 2 and 3, let's subtract that here, subtract 24 here, that term goes away, which is what I wanted it to do. I've sort of got 3 equations with 2 unknowns. That's a clue that this question, there's something going on. That it's not just random numbers being thrown at us, that there's something cleverly chosen so that works out. A little bit like having 3 equations for 2 unknowns, and sort of magically the third one just worked out anyway. Okay, right. So you could have looked at these blue terms instead of looking at these green terms. Could have looked at the xn yn coefficient instead of the yn squared coefficient. Okay, I really like the next part of the question. I'm going to erase most of this. What do I want to keep? I want to keep up here, we thought that x1 equals 3, y1 equals 2, that was our solution here. And over here we thought we wanted we want a equals 2, b equals 3 over here. Okay, next part of the question says find, and it doesn't say how, find a pair of integers big X, big Y, which satisfy big X squared minus 2 big Y squared equals 1, and they want big X to be big, they want it to be bigger than big Y, and they want big Y to be big, they want big Y to be bigger than 50. So we're looking for big numbers that satisfy X squared minus 2Y squared equals 1. Oh, what's the rigorous proof? Somebody would like a rigorous proof through to part 2. I suppose through to part 2, scrolling up very quickly. Here we just found a pair of integers, found a pair of positive integers. That was fine. Part 2, I think we just tried our luck to see. Well, this seems a bit unlikely. Can we find any numbers that work at all? 2 and 3 work for the xn squared and the yn squared coefficient, and then you can check that in fact with this definition with 2 and 3, this actually works. Everything simplifies through just the way you want it to. Callum's here. Callum's got a pair of numbers that are absolutely enormous, and they're definitely bigger than 50. Callum, I think, might have been here in the previous math workshop. It's been working out bigger and bigger numbers ever since, I think, perhaps, if I recognise the username, or maybe Callum's ahead in this question. Let's be fair. It might be a different Callum. Okay. Is it important that the coefficients are 1 less than those for xn plus 1? That has come out. The numbers are 3 and 4, and then 2 and 3. Let's look back up here. I'm going to write the bit. I think we've all got an understanding of what we're doing next. X squared minus 2y squared equals 1. For big X and big Y, really big numbers that do that. So, how long are those numbers that Callum's put in chat? Callum's put some enormous numbers in chat. Right, okay. You had to wait. If you've come back from the last one, you've had to wait about 45 minutes for me to get to that point again. Right, okay. I like this part of the question because we could go and think about trying some numbers again. Just try some bigger numbers that are larger than 50 in here. Or we could try and understand the previous part of the question. So I've been trying to hint that it's not just random numbers flying around. There's something going on here. Oh, and I suppose that's why someone's told me the numbers 3 and 4 are bigger than 2 and 3 by 1. That's true, and that is a link. It's not quite what I was thinking of. There's some reason why, as we were doing the algebra, we didn't have to understand what this equation was or what it was for. It could have a 10 here and a 9 over there, and we would still be able to just sort of blindly turn the handle, do the algebra, work out the numbers. Somehow for this next part of the question, I'd like us to go back and actually look at what this says and what this means. Because hiding in here somewhere is the sort of structure of quite a nice question. Sometimes it's right to stop doing maths and think about what's going on. This part of the question really rewards you for stopping and thinking. Right, somebody's asked about, I don't know if you're in the workshop or if you've just asked the question. I sort of worry a little bit if people are just using the Q&A while we're shouting about numbers of A and B. That might be quite confusing, but never mind. If you're in the workshop, it doesn't matter. It's totally fine. You can do maths in year 12, further maths in year 13. Fine with us. Doesn't matter when you certify it. I'm going to type that response as well in case you're not here. If you're not here, you haven't heard me say that out loud, but I guess I'm going to stop talking and type an answer. turns out I misread the A-level question that just came in. Just in case the person's in this workshop as well, I misread your question. You wanted to know about, you're doing further maths in year 13, which is fine with me, but you're worried about getting a predicted grade. I think it's going to be fine. I think your teacher's going to be able to give you a predicted grade based on what they've seen from year 12. Certainly lots of people do maths in year 12, further maths in year 13, and then end up with a predicted, apply with a predicted grade. I think that might be difficult for the teachers, but in some sense, they know that you're doing maths in year 12, further maths in year 13 at your school, so that should be fine. When you make an application, you list the qualifications you haven't done yet, and your school is asked for a predicted grade in those. It's not a problem for us, shouldn't be a problem for them. Okay. Ooh, so there's different suggestions. People have got some numbers down here for X and Y. People are saying 99 and 70, which are huge numbers. I like this because you could guess those. Well, sort of, maybe. You could guess numbers until you guess those. It would be quite slow. But there's a way to calculate these without worrying about what the square of 99 is. Or even Callum's back with another huge number, which I don't think Callum has squared. So somehow working out that these numbers without squaring 99 or 70. Okay, and the trick is to understand what this thing I'm boxing now, what this actually means. So this says, it's actually quite a nice expression. If you squint at it and ignore the subscripts, this says something like x squared minus 2y squared in terms of the n plus 1 variables is equal to x squared minus 2y squared in terms of the n values of the series. So I suppose that says that x2 squared minus 2y2 squared is equal to x1 squared minus 2y1 squared. And then the next row down, when I set n to be, this is what happens if I set n equals to 1. And if I set n equals to 2, then I'll get x3 squared take away 2y3 squared. That's going to be equal to x2 squared minus 2y2 squared. So hang on, all these things are sort of equal, that they kind of chain together to say, hang on, as I work out this series, what I'll get is, at each step, x squared minus 2y squared, for those values of the series, is equal to the previous value. So if I choose x1 and y1, so that x1 squared minus 2y1 squared is equal to 1, which is what we did, if I do that, then I'll get a series of pairs of numbers which have x squared minus 2y squared is equal to 1. The thing you're actually doing here is making sure that x squared minus 2y squared is the same as you go through the series, so that if you start with it equal to 1, then it will stay being 1. Okay, all that means is we just need to work out we just need to work out some terms of this series. So I need to use these equations to work out some terms going through. What am I doing? So a is 2. Oh dear, it looks like I'm going to have to multiply. So 3 times 3 is 9, plus 2 times 4 is 8, that makes 17. And y2, using this equation with a and b, it's going to be 2 times x1 is 6, plus 3 times 2 is 6, that's 12. So I get this new pair, and brilliantly, 17 squared minus 2 times 12 squared is equal to 1, because x squared minus 2y squared stays the same as you do this. Okay, so we're going to substitute in the previous values and keep going. We can repeat this. So this is some new larger values that satisfy the same sort of equation. If we keep doing this and we work out x3, y3, I think they turn out to be 77, or they turn out to be 90 and 77 in that order. I'm using these equations again to work them out. Yeah, use the equations, George has got it, use the equations for x n plus 1 and y n plus 1 to find bigger numbers starting from x1 and y1 and build up. These are sort of a series defined, okay, it depends on the x and the y values, but it's defined in terms of previous values. So we can build this up. And we can keep going to find these numbers are bigger than 50, but we can keep going, which is what Callum is doing. You can keep working out more and more terms of this series to get really big numbers that satisfy this equation exactly. So let's stop a moment. We've found loads of solutions now that satisfy big x squared minus 2 big y squared is equal to 1. It's not clear whether we found all of the solutions, all of the pairs of numbers x and y that can do that. Maybe that's something to go and think about afterwards. not really sure how you would think about that. It's just something that I've thought of. Okay, so this part wants us to think about using the values of a and b we had. Last part of the question now. What's the approximate value of xn over yn? And I guess I'm going to let you think about that for a moment. You should also let me say if the explanation for 3 didn't make sense there. I did it slightly weird order. It's all linking things together. So you're keeping x squared minus 2y squared constant. Okay. What do we think happens to xn over yn when n is really big? I'll talk and ramble a little bit while you're thinking. I like both of these parts because they test whether you understand what was going on in the previous thing. So in parts 1 and 2, the question setter has come up with something clever, a way of generating new solutions to this equation. And in part 3, they sort of want to check whether you can spot that, that's what we're doing. We've generated new numbers that happen to all have x squared minus 2y squared equal to 1, because that's what that boxed equation did. It checks that everything was staying the same as we went up. And I like part 4 because it's also checking, just making sure that you understand that xn and yn satisfy that equation as well. It does look like root 2. Somebody says root 2. Some sort of, okay. An anonymous person is helping me out by trying to work out if these are all the solutions. Some sort of squeeze method. Sort of bounding solutions between pairs of solutions that we've got, I suppose. Yeah, something like consider 2 solutions you've got, do some sort of difference between them. Yeah, as the numbers get large, I like that people are finding different ways to phrase this in chat, so I might let that roll for a moment. As the numbers get large, the +1 is pretty much irrelevant. I like that. The 1 is negligible. So x squared is roughly equal to 2y squared. Yeah, I like this. I think there are a few distinct steps that we should go through here. So with these values of a and b, we know that xn squared minus 2yn squared is equal to 1. Okay, so we need to say we're using those values of a and b, and we know that we get 1 because of the argument we just had about it always being the same number when it starts at 1. This is sneakily a little bit like proof by induction, right? We've got a thing that starts at 1 and it stays the same. So by induction it stays equal to 1. But you don't need to know about induction for that to make sense. With these values of a and b, we know that xn squared minus 2yn squared is equal to 1. We also know that because a and b are positive, I guess they're bigger than 1. Because they're bigger than 1, xn and yn get really large as n increases. I don't know if there's a mark for saying this, because maybe it's obvious that xn and yn are getting really large, but you're multiplying things and adding them together. It's getting big, right? Because everything's bigger than 1. I'm worrying a little bit here about things being smaller than 1, but multiplying things by 2 and 3, maybe I shouldn't worry. Xn and yn are getting really large. That means that what do I want to say? Let's put it like this. Let's say that xn squared is equal to 2yn squared plus 1, but 2yn squared is bigger than 1, much bigger. So xn squared is approximately 2yn squared. And now I'm in business because I can rearrange to get yn squared is about 2, so xn over yn is about root 2. I think that's good enough. Good enough for me here in terms of explaining how that 1 is much smaller than the big numbers xn squared and 2yn squared. I can imagine harder problems where it's a little bit more subtle about what actually happens when these numbers get big. But hey, you got a big thing is equal to 1 more than a big thing. These big things are pretty much the same size, aren't they? Okay, so that means the ratio looks like root 2. So actually, as well as generating solutions to this equation with this method, we can use our values of xn and yn to get an approximation for root 2. So if I take some of the enormous numbers that Callum has been throwing in, we can, Callum's even put some code in chat as well now. If I set some of these numbers that Callum's been putting in, I can check that the ratio of those things should be a good approximation for root 2, which is nice. And there's some code in chat now as well. Define recursive numbers n x equals 3, y equals 2. I don't understand code. There's a colon. I'm trying to read out code and I don't know what's important. If n is 1, return xy. Return. It's recursive. Ah, right, okay. There's some recursion going on. I don't know what's going on. There's some recursive code. In the last workshop, I suggested that people go and code this up, so I'll suggest that now as well. If you know about how to make computers do things, then you might like to play with making a computer do things to work out values of x and y. You could, if you like, check that they do x squared minus 2y squared equals 1, even when you're making huge numbers, and maybe check that the value goes to root 2. Other problems we could try as mathematicians is we could think about other equations. So if I change this number 1, if I change this to something else, then how much of the maths do you need to change? What's the same and what's different? If I change this 2 to something else, what's the same and what's different? That one's much harder. So there's something clever going on in this question to set up these set up these relationships just the right way, so that you keep getting solutions to the equation. If we could do that in general, that'd be pretty good. Somebody in chat has said that there's a name for these. If you want to read more about them, I think it's called Pell's equation. None of this is necessary for doing the maths. We've moved beyond Math Workshop now into maths. So if you're interested in this sort of maths, then there's more stuff you can read about it there. Okay, I quite like these long questions because quite often they get you to do something, so you get some marks for doing it, but then also give you some marks for understanding what you're doing, which is an important skill to have as a mathematician. So you might look at things and work out, you can charge through this algebra, but then can you stop and think about what was going on for the second half of this question, understanding what you were doing in the first half of the question. Okay, that'd be worth 15 marks overall. As we said, that you do 4 long questions, score 60 on your long questions, 40 on the multiple choice questions. That adds up to 100. That's just about it for maths, I suppose. We're getting up to the end of time here. If there's anything else I should have said that I've forgotten to say, please remind me now. It's called the Mathematicians Test. I said that right? It's a maths test that people do for admissions. Okay. We'll be running, if you like this sort of thing, then you might like the Oxford Online Maths Club. Every Thursday we do little maths mini lectures, bits and pieces of problem solving. At some point later in the summer, that's going to turn into a math live stream where we focus on math problems and just do things a bit like this with a chat open and people doing math questions, chatting about them, talking about strategies. Oh, I haven't said how long you get. Thank you, Phoebe. It's a 2.5 hour test. It's 2.5 hours, and yes, which might be a bit longer than other tests you do. Has anybody ever got 100%? 100% is very rare. Very, very rare. I think nobody got 100% last year. Nobody needs to get 100%. The average mark on the test is somewhere around about 50 most years. We do it. It's really tough because we need to use the test to help split out people who are really great at maths like you who are doing this test. So we have to make the questions really hard. If everybody gets 100, it's not useful to us. I mean, it's great, but it's not useful for us to deciding who to shortlist. Maybe says we could have made the questions a bit harder. The average is about 50. A good score is about 70 most years. About 70, 75-ish would be really good. There are more stats and more past papers and more maths everything on the maths website, www.maths.ox.ac.uk/r/MAT, which stands for worldwideweb.mathematics, short maths, short for mathematics, OX, short for Oxford, AC, short for academic, UK, short for United Kingdom, R, short for redirect, within my website, MAT for Mathematicians Test. And if you can remember all of those abbreviations and acronyms, then you can find as many past papers as you like and solutions and statistics on what the average score was for previous years, including, if you dig deep enough on that website, histograms of what the score distribution was. Oh, and somebody's put a link to that in chat as well. Thank you. People have been very helpful in chat today. There's no hard cut-off pass mark on the MAT. It's just one thing that we use when deciding who to shortlist. In general, the more marks you get on the MAT, the better. But we also look at the rest of your application. So we don't have a hard cut-off. More marks, the better, please. How many method marks can you get? Well, so the mark scheme breaks down. How many method marks can you get? The mark scheme breaks down where you can get method marks and accuracy marks. Or the mark scheme that Accuracy the Markers does. I guess you could probably get up to, let's say, up to about 10 or 11 marks, probably, on a long question without getting anything right. But having good ideas and methods, if you really tried, like, you'd have to make a lot of minus sign mistakes. And, oh no, I didn't get that quite right either, but then only lose 1 mark. So you get a chunk of the marks by having good ideas. And do other universities require the MAT? Yeah, it's also used by Imperial College London and by the University of Warwick. Imperial, I think, strongly recommend it to the extent of nearly, but not quite requiring it. Warwick University recommend it or accept it as one of the maths tests that they accept. You should talk to Imperial College London and Warwick about their policy on MAT if you want other universities' opinions on the MAT. Good. I think that wraps up this MAT workshop. Since the broadcast this morning, I've made a thanks for watching slide rather than a going live slide, so always improving the live stream experience. I'm going to be back at 4 o'clock, so in half an hour, to do a last wrap up of the open day, answer some Q&As, some good questions coming in here, but I'm going to take half an hour of not being live, thank you. 4 o'clock, back for some Q&A and next steps. That's over on a different link back on the open day page. You've got about 27 minutes, which I think is long enough to watch one of the mathsy sort of videos from the bit in there, like Infinity Machines, or the first half of, you can probably fit in Applied Mathematics or something like that. And at 4 o'clock, live for a bit more Q&A and next steps, wrap up. Everyone back together again. Right, okay, enjoy the rest of the day. See you around. Thanks for watching. I'm still not good at stopping these. Right, let's click this.